Hello, welcome to Tech Engineering. Today we're going to take you through the design of a retaining wall in Prokon 2.4. Once you have pressed on your wall, first you must select concrete, press on wall, and then it opens up here. Here you have retaining wall design, and you can input your parameters at this section. The first thing you do is, let me do that. The first thing you do is change the title. Let's say cantilever retaining wall. After your title, you have to check on the type of the wall. Prokon allows you design three types of walls. The first is the propped cantilever, and that is what opens up by default, as you can see. And the second one is the cantilever and are simply supported. So today we are just going to design a cantilever one. After that, you choose the theory of design you want to use. We have column theory and Rankin's theory. Rankin's theory is normally does not use friction between the wall and soil, but Coulomb assumes that there could be friction between the wall and the soil, and actually it's the recommended, even if it could be tedious whenever you're doing manual calculations. And if you want to know the differences in the two theories, is that Rankin considers only a vertical wall that is frictionless, but Coulomb considers a wall that could be inclined, or the soil could be inclined with relative to the wall, and friction in the wall is also considered. There are also a few other differences in these two theories, though Coulomb is preferred. Therefore, normally use Coulomb because it gives the most accurate result, as it also designs to elastic equilibrium as compared to Rankin, which is used to design to plastic equilibrium. Back to our design, we have already chosen Coulomb theory, and we now get to entering of our dimensions. As you can observe from up here, whenever I enter a dimension, let's assume h1 is normally the total height of our wall, and whenever I enter the total height, let's say it's 3, our sketch disappears, and then I want to bring it back so that we are properly guided as we do the design. So I have opened another window of the same retaining wall design. So h is normally the total height of our wall. h2 is the height of the soil in front of the wall. As you can observe, in front of the wall we have a cantilevered section, and then the height of the soil at that section is known as h2. So let me assume a height of 300 millimeters, that is 0.3 meters. h3 is actually the height from the top of the wall to soil level at the back of the wall. As you can observe, from the top of the wall, the soil level at the back of the wall at this section here. So I'm going to assume my h3 as 500 millimeters, as you can observe there. And you will realize that as we continue adding the parameters, we model our retaining wall, and it will appear almost as this one at the end. HW is the height of the water table, which is normally measured from the top of the wall, and its dimensions from below the wall. So if there is a water table, let's assume we have a water table at a height of 2 meters. So we are going to say 2 meters from the base, from the lower side of the wall. So HW, let's use 2 meters, and you will observe how it will be modeled here. We have already modeled h1, h2, hw, and h3. You can observe that hf is the height of the support point from the top of the wall for a simply supported or a propped cantilever wall type. So because our wall type is just a cantilevered, therefore we don't have is either a support or a load at this section. That is why this is disabled. If we have, for instance, in this sheet, it is a propped cantilever that is supposed to be designed, and you can observe that we have R, and this section is enabled. And because we are designing a cantilever, therefore we can not enter that value because we don't have a load at this section. We also go to B. B is the horizontal base dimension in front of the wall. As you can observe, it here is the distance from this to that. And let's assume we have 600 millimeters at that section. That is 0.6 meters. And D is the section at the back, the horizontal base dimension at the back of the wall in meters. Let me assume I have 2. It is normally longer. It is modeled longer than B because the weight of the soil causes a clockwise rotation of this retaining wall. Whereas to the force that is trying to cause turning in the retaining wall. So they will all cancel out. That is why we cantilever it at that section. So as you can see, it is already coming up. I have not entered the width of my wall. That is why I'm not able to observe it here. And on observing, C is normally the depth of the base, as you can observe in this section. And let me use a C of maybe 0.5 meters. It has already been modeled. F is the depth of the shear key. If I have a shear key at this section, I normally input its depth at this point. But whenever you're designing a wall, first of all, you need to design it as a cantilever, and then if it fails against sliding, therefore you provide a shear key. Therefore, at this section we are not going to provide the shear key, and therefore we will not enter the values of F and XF. But for the modeling, for the sake of modeling, we will just enter a value so that you can observe how it will appear. So let's assume a value of 0.2. It has already been drawn, but because we have not entered the width and the location, it has not appeared. And XF is normally the position of the shear key that is measured from the front of the base, from here to this section. That is XF. And this section was 600. Therefore, I want my shear key around 1.3 meters from this section. So 1.3, I had 600. I had 0.6. That is going to be 1.9. Sorry, I'm not able to enter that now. But let's oh, that is too far. Let's enter it maybe at a distance of a meter. And as you can observe, it has been modeled there. The reason why I'm not able to get the other values is because they are not put in the library for these small walls. But if that is the case, if I want my 1.9, still I could enter it manually like that, and hope you see where it appears. It is slightly far. Let me change it to 1.5. Yeah, I want it there. Now we move AB. From observation, you can observe AB is the width of our wall. We have not entered 80. 80 is the width of our wall at the top section, and AB is the width of our wall at the bottom section. Sometimes, because there is a lot of pressure acting at this bottom section, we have more width at the bottom than at the top. Therefore, my top will have a width of 0.25 millimeters. Then my bottom will have a width of 4. And from observation, you can see how it appears. There, at this section, I'm also allowed to enter the cover of reinforcement. Then I want to use, because a retaining wall is almost like a foundation, I'll use a cover of 50. Therefore, I'll use a cover of 50 for my walls and a cover of 50 for my base. Or because the base is submerged and the wall is standing, I can use 40 for the wall. And remember, cover design is normally guided by the exposure conditions. If you have a lot of sulfates or any chemicals that could corrode your steel, therefore you have to consider that into your design. From there, we move to this section. This section is where we enter our loadings, and W, P, XPL, LH, and X are all highlighted at this section. For instance, XL is a point load acting at a distance from this, and we don't have it, so we will not have a value there. LH and R from observation, they are these loads acting horizontally to that section. We will also not have a value. And P and X, all those are point loads that are acting at that section, and we are not going to enter any value there. Although you realize W is in kilonewtons per meter squared, this is the load of this upper section that is acting at this upper section, and let me assume a load of 5 kilonewtons per meter squared, and you see it is distributed there. If I enter 10, it will also be distributed there. Yes, and if I need to use a P, if I have a value of P, I can say I have 5 kilonewtons. Then I have to input the distance, or it will act at the face of the wall. Therefore, let me say at a distance of 1 meter from this point. And as you can observe, it is already there. I can also do that for L. If I have 7 kilonewtons per meter, which is normally a UDL, and it will act up to a distance of, let's say, 1.2 meters. You can see that it will act at that point. That is the resultant point of action. And I would also do that for LH, though I do not have any horizontal load acting at my wall. If it could be a prop or these other simply supported, then I could have loads at that section. I move to general parameters and design parameters. And the first one is the soil friction. We have different angles of friction for different soils, and that one I would like to take us to this. And soil friction angle actually is normally a shear strength parameter of soils, whose definition is derived from the Moore-Coulomb failure criterion, and it is normally used to describe the friction shear resistance of soils together with their normal effective stress. In the stress plane of shear stress effective normal stress, the soil friction angle is normally the angle of inclination of the failure envelope with respect to the horizontal axis of the Moore-Coulomb shear resistance line. Therefore, I have done a small sketch here. Let me increase its size so that you can see it. You see, whenever you have developed your Moore equations and circles for your soil, and this is, you plot the normal, the shear stress against the normal stress, and obtain the failure envelope from this circle. Therefore, the angle of inclination of the failure envelope is normally the angle of friction of soil. And these parameters at this section, you normally obtain them from the geotechnical report done by a geotechnical engineer. And whenever you're designing a retaining wall, kindly do a geotechnical investigation so that you determine these parameters. For the sake of this class, I'm going to give us a general angle for general soils. We have sand, and its cohesion is normally 0, and the internal angle of friction is either 30 or 35 depending on the condition of the soil. So if we are designing a retaining wall to retain, let's say, sand, we can use 30 to 35 depending on the conditions on the ground. So for this case, we are going to adopt 30. Let me open both so that we are able to see as we do the modeling. So let me use a value of 30. And we also have a field slope that is beta. This is the slope of my wall with relative to the soil. So let me use an angle of 10, and you observe what will happen. Look, the soil is at an angle to the wall. And if I increase it to 30, observe what happens. Yeah. So if I have a retaining wall that is like that, that is what I should do. We also have wall friction because this is Coulomb. Coulomb uses wall friction in the design, and we also need to determine the friction resistance of our wall so that we design for that. So for this case, I'm going to pick, let me use 25. From there, we move to the density of concrete. This is the density of concrete. We normally use 25. It is 24 for mass concrete. And whenever we have steel, we call it reinforced concrete. Reinforced concrete has a density of around 25% kilonewtons per meter cubic. From there, we move to the density of the soil, this soil that we are retaining in the back of the wall. And we can use, let's say, if it was sand, we can use a figure of 18 kilonewtons per meter cubic. But also, from a geotechnical report, kindly determine the density of your soil. FCU is normally the class of concrete you're designing for, and from the British standard, we could choose class 16/20, that is class 20, or we could use class 20/25, which is class 25. So in this case, let's assume 25. FOI is the grade of your concrete, and we're going to use for 60. Sorry, not the grade of your concrete. This is the grade of your steel. We either in Kenya, where I'm doing this video from, we normally design for 460 or 500 because that is what is readily available in the shops. But you could get different grades depending on different utilities. Therefore, having talked about the general parameters, we now move to the design parameters. In the design parameters, we have this SF of overturning is the safety factor overturning, and we normally prefer a value of 1.5 this case, and for slip I normally design for safety factor of 1.5. And these are also ultimate limit state factors, and according to the British standard, for the dead load we use 1.4, and for the live load we use 1.6. Then Pmax is also very important. This is the bearing maximum bearing capacity of your soil, and we have different soils with different bearing capacities. From observation, it's here. And remembering that we designed for sand, from observation, medium dense sand has 100 to 300 kPa of bearing pressure. Therefore, let's choose 300. That is it. Let me open board. Yeah. So let's use 300 kPa. There you go. The soils Poisson's ratio, you also get it from the geotechnical investigation, but I have prepared these for this class, specifically for this class, and because it was sand, the Poisson's ratio is from 0.25, from 0.15 to 0.4, and this is how they are defined. So if I assume that I was using dense sand, I'm gonna pick a value of 0.2. Remember, these values are supposed to be obtained by in the geotechnical report provided by your geotechnical engineer. Or if you're the only engineer on site doing the project and you do not have experience on the design of that triangle, kindly carry out geotechnical investigation before you proceed to design your retaining wall. Therefore, we have been able to enter all this. Also, we have dead load factor for overturning. You realize we have the soil and the wall. Therefore, this is where we enter our factor for overturning. And in this case, I normally prefer factor of 1.0, but also it depends with the conditions of the wall you are designing. Having done all that, we also had an input in the title. You can do loads due to seismic analysis by just checking this table to enable this. Therefore, you can put the vertical and horizontal acceleration and include your live loads at these sections. And then you can observe. You can even enter the values manually, but in this case, I'm not going to do seismic analysis. And you can also do your user defined design values. You can use the values that are generated by default, or you can click there to enter your values. So as you can observe, this is my wall. This is what I modeled, and we are done. If I open on symbols, this is the same as whatever we are seeing here. Therefore, we are done with our inputs. The next thing is to come to the design diagram, and from there it is able to give you your values. It will tell you the wall type that you choose, the theory that you are using in your design, and it will model for you your shear force diagram. And then from observation, you can observe V is equal to 41.8 kilonewtons. And then the active and passive earth pressures are also given. These are the coefficients. The angle of internal friction, 25 degrees is here. And this was 5 degrees, the angle of inclination of the soil with respect to the wall. And these values that you also had inputted at this section are also given here. It will also give you the position of moments, the areas of steel that are required, and so on and so forth that you might need. At this section, it also shows you the dimensions and your design code. You move to moments and reinforcement. At this section, it gives you the moments, and you can move your cursor, and it will give you the height and the moment as you move your cursor. But down here, it highlights for you the maximum moment, and it also shows you the position at which the moment is maximum. Wall reinforcement is also required here. It shows you the required maximum wall reinforcement. The base moments are given in this section. These are moments for your walls, and these are moments for your base, and it will also give you the required reinforcement and the maximum moment. All these are dependent on the values that you had entered at this section. And also from there, you can proceed to calculation sheets. At this section, you can go to output settings, and you determine what you want to appear on your calculation sheets. But before you go to calculation sheet, we normally go to the bending schedule so that we are able to observe our bars and how we are going to fix them on site. Because we are done with this one, let me close it. Yeah, maximize this. And from observation, you can see your bars have been highlighted there, including bars at the shear key. You can also manually edit these bars. If I want to use 16mm bars, you can observe these changes. This shows you the required reinforcement. This is the nominal, to mean the minimum that you can provide at that section, and this also shows you the one you have entered. Prokon automatically generates for you an economical one, but if you want to edit it, you can do as I have detailed. So for instance, if I want to change this to a 10mm bar, you see it is less than the nominal, even if the required is 0. Therefore, at this section, we have to use 12mm bars. And let me see if I'm using that. Let me say 12 instead of 16. You can observe it is below than the nominal, even if it's greater than the required. Therefore, we have to always provide something that is greater than both the required and the nominal. Therefore, I can reduce the spacing to 150. You can observe it is more than the required. Therefore, you can also play around with that. And if you want to generate the bar bending schedules and the drawings for your site works, you generate the schedule and open Prokon pads so that you are able to edit that. And also you can change a few things here and there. This is the cover of your walls and on stress, and if you don't want to change them, you can leave them as they are in default. Now the bars have been detailed for you as observed. You can see this is a section. Yeah, this is a message obtained because I was I had generated enforcement and it has shown me where it is. Therefore, we are done with the design of our wall, and you can observe the details as highlighted here. These are the details. And on observation, HOR, if you do not know, HOR means horizontal bars. These are the bars that are running in the horizontal direction from observation. They are detailed in the right way. NF means the near face. These are bars at the near face. FF means the far face. And I think there is another one. EF means each face. And starters are also the bars that are going to be starters for your retaining wall that will lap the other bars. Also, the development length of your bars is also determined, and you will obtain that in the bar bending schedule. If you want to see how you can open the bar bending schedule, the pads, Prokon pads, to see your bar bending schedule, kindly subscribe to this channel and keep watching our videos. We will do a video of how to edit your drawings in Prokon pads. Therefore, thank you very much. I hope you have learned a lot. And if you have a question, kindly drop it in the comment section below, and like our video, share it to friends so that they also learn of this important retaining wall design module in Prokon. Therefore, may the good Lord bless and keep you, and hope to see you another time.